So hello everyone, welcome to the first part of tutorial 6. Let's start with question number 1. Question number 1, we are supposed to find a recurrence relation for the number of strictly increasing sequences of positive integers that have 1 as its first term and n as its last term. Okay, where n is some positive integer, right? So for instance, if n equal to 1, then there is only one sequence which starts with 1 and ends with 1, and which is a strictly increasing sequence, right? Whereas if n is equal to 2, then also I have only one sequence starting with 1 and ending with 2, and which is strictly increasing. By the way, I mean by strictly increasing sequence, I don't mean that I need all the numbers between 1 to n appear. Similarly, if n is equal to 3, then a possible sequence could be starting with 1, ending with 3. This is a strictly increasing sequence. Or I can have a sequence where I have 1, 2, 3, starting with 1, ending with 3, and having 2 in between. Right? So these are the various sequences possible for different values of n. Now our goal is to find out a recurrence equation uh, for this problem. Okay. So basically what we are asking here is the following. Imagine you have an arbitrary sequence, okay, starting with A1, ending with AK. The restrictions are here that the first term should be 1, and namely A1 should be 1, and the last term A of k should be n. And in between you have the numbers A of 2, A of k minus 1, where they appear in the strictly increasing order. And they can be any numbers from the set 2 to n minus 1. Okay, so let S of n denotes my function, which is the number of valid sequences ending with n. So a trivial recurrence condition for S of n is the following. I can say that S of n is the summation of S of 1 and S of 2 and all the way to S of n minus 1. This is because the second last value here in the sequence, namely A of k minus 1, can be 1. If that is the case, then basically what I am saying is find out all possible sequences starting and ending with 1 and append it with the value n. That will give you one category of valid sequences starting with 1 and ending with n. How many such sequences you can have? You have S of 1 such sequences. Or your A of k minus 1, namely the second last value in this sequence, can be 2. In that case, what I am saying is you find out all valid sequences starting with 1, ending with 2, and which is a strictly increasing sequence. And in each such sequence, you put an end at the end. That will give you another category of strictly increasing sequences starting with 1 and ending with n. How many such sequences you can have? You can have S of 2 number of such sequences. And the same way, your second last value in the sequence A of k minus 1 could be n minus 1. So basically I am saying take any valid or strictly increasing sequence starting with 1, ending with n minus 1, and put an end at the end. That will give you another category of strictly increasing sequences starting with 1 and ending with n. And you can have S of n minus 1 such sequences. And all this category of sequences that we have discussed, they are disjoint. So this is one of the recurrence conditions for our function S of n. But we want a more compact uh, recurrence condition. Compact in the sense the degree of this equation that we had just formulated, right? What its degree? Its degree is n minus 1 because S of n depends on, or that because the nth term of the sequence that we had formulated here depends on n minus 1 previous values in the sequence, right? We want a more compact recurrence condition. So let's derive that alternate recurrence equation. And this alternate recurrence equation is derived by using the following argument, right? So imagine you have considering a valid or strictly increasing sequence starting with 1, ending with n, and the second last value in the sequence is a of k minus 1. Now, there can be two categories. Category 1, that your a of k minus 1 is n minus 1. Okay, that means you are considering all such strictly increasing sequences where the second last term is n minus 1. How many such sequences you can have, right? You can have s of n minus 1 such sequences, and you take any such sequence and append it by a value a of k equal to n, you get a strictly increasing sequence starting with 1 and ending with n. And there will be s of n minus 1 such sequences here. Okay? Category 2 is the following. The second last value, namely a of k minus 1 in your sequence, can be either 1 or 2 or n minus 2. Right? And you end this a of k minus 1, you append a n at the end of this a of k minus 1, you get a valid or strictly increasing sequence starting with 1 and ending with n. Now what we can do is we can interpret the n which is there at the last position. Last position means after a of k minus 1 in your actual sequence ending with n. We can interpret this last n as n minus 1. It's just some mental interpretation. Okay. So for instance, what I'm saying is here is one of the strictly increasing sequences in category 2. Why? Because my second last value, namely a of k minus 1 here, is n minus 3, right? It is not n minus 1, it is n minus 3. And then there is a following, there is a n following this n minus 3. So I can just view this sequence as another sequence where instead of n being appearing at the last position, I have n minus 1 appearing at the last position. Mind it, I stress here that these second category of sequences are different from the first category of sequence. Because in the first category of sequence, I have only n minus 1 allowed in the second last position. But in this category 2 of sequences, I am not allowing n minus 1 in my second last position. My second last position could be anything from the set 1, 2 or n minus 2, and then the last position is uh, occupied by n. What I am basically saying is that just treat that instead of being n having at the last position, you have n minus 1 at the last position. Okay, and it's easy to see that how many such sequences you will have. By doing this logical interpretation, that means by substituting the last n with an n minus 1 in your mind, you can easily see that there will be s of n minus 1 such sequences. And also, this category 1 of sequences and category 2 of sequences are disjoint. And you can't have any third category of strictly increasing sequences because your second last position, namely a of k minus 1, could be either n minus 1 or different from n minus 1. And these are the only two possible cases which we have considered, and hence we can say that our alternate recurrence equation will be s of n equal to twice s of n minus 1. Now, this is an equation of degree 1 because now the dependency of the nth term is only on the previous term. So definitely this is a better recurrence equation in terms of solving it and in terms of the number of initial conditions that we need here. It turns out that even though this equation, this alternate recurrence equation is of degree 1, we need two initial conditions, right? So S of 1 will be 1. This is because if n is equal to 1, there is only one sequence which is strictly increasing starting with 1 and ending with 1, namely the sequence 1, right? Namely the sequence which is having only the value 1 in it. And if I take n equal to 2, Then also I have only one sequence which is strictly increasing, starting with 1 and ending with t, and this 2. The sequence will be 1 followed by 2. That's why s of 2 is equal to 1. Now you might be wondering that why s of 2 I have to explicitly specify it as an initial condition. Why can't I just have an initial condition s of 1 equal to 1, because this is an equation of degree 1 here. This is because if I don't explicitly specify the value of s of 2 equal to 1, and then if you try to derive s of 2 by substituting n equal to 2 in this recurrence equation, you should get s of 2 equal to twice s of 1, which is 1, which is equal to 2, which is not the case, because you don't have two strictly increasing sequences starting with 1 and ending with 2, right? You have only one strictly increasing sequence. Or does that mean that our recurrence condition that we have derived is wrong? Well, that's not the case, because if you see here, right, the problem that is happening here is that if I take n equal to 2, then this case 2 or category 2 of strictly increasing sequences won't be there at the first place, because for n equal to 2, this case 2 boils down to saying that at the second last you have 1 at the beginning, and your a of k minus 1, namely the second last string, could be from the set 1 to 0, which is not the case, because n minus 2 for n equal to 2 will be 0, which is not well defined here. In the sense, n minus 2 is 0, and hence you can't have a second last position occupied by something, say 0. That's not allowed, right? So that's why case 2 or category 2 is not going to occur for the case of n equal to 2. For n equal to 2, it's only the case 1 which can occur. Namely, your second last position can be occupied only with 1. And then you append it with 1. That's why you have only one valid sequence for the case of n equal to 2 as well. It's only from n equal to 3 onwards that your category 2 of strictly increasing sequences appear, right? And that's why we have two initial conditions needed. Okay. In question 2, you have to find out a recurrence relation for the number of bit strings of length n that contain the substring 000, right? It might have more than one occurrence of 000 as well. In fact, a string of length n consisting of all zeros is a valid string. Okay, so let's try to find out this by formulating a recurrence equation. So let S of n denote the number of bit strings of length n containing the substring 000. So what we will do is, instead of counting the number of strings containing 000, we will rather count the number of strings of length n not containing 000, because it will be relatively easier to formulate a recurrence equation for the number of bad strings. Bad strings in the sense they do not have an occurrence of any 000. So I call or I denote the sequence of all n length of its strings not containing 000 by this B sequence, and B of n is the nth term of such a sequence. Now it's easy to see that as per the definition of S of n and B of n, the nth term of the S sequence is nothing but 2 to the power n minus B of n. This is because 2 to the power n is all possible n-bit strings. Okay, it's a set of all possible, or the number of 2 power n basically denotes all possible n-bit strings which has an occurrence of 000 and which do not have an occurrence of 000. And you subtract from such strings all such strings which do not have an occurrence of 000. You will get the number of strings of length n which has an occurrence of 000. So our goal now will be boiling down to find out a recurrence condition for the B sequence. And it turns out that there are three categories, and more specifically three disjoint categories of bit strings of length n not containing 000. Let's look into those three categories. Category 1, for those strings of length n, okay, which starts with 1, right? If it starts with 1, then in order that the overall string does not have any occurrence of triple zero, it should be the case that the remaining portion, namely the remaining portion of length n minus 1 bit, should not have any occurrence of triple zero. How many such strings we can have? As per our definition of B function or B series, there will be B of n minus 1 such strings. So this is category 1 of bad strings. Category 2 of bad strings, which starts with 0 followed by a 1, right? And if that's the case, then the remaining n minus 2 bit positions should not have any occurrence of triple zero. How many such bit strings we can have? We can have B of n minus 2 such strings. And category 3 of bad strings, where the first two positions are 0, and in that case, the third position cannot be 0, because if the third position has a 0, then it's not a bad category, bad string, right? Our definition of bad string is that it should not have any occurrence of triple zero. So in category 3, we are considering the case where the first two positions are 0, the third position is 1, and after that, in order that the overall string do not have any occurrence of triple zero, the remaining substring of length n minus 3 should not have any occurrence of triple zero. How many such bad strings I can have? I can have B of n minus 3 such strings. And these are the only three categories of bad strings, right? I can't have any other fourth category. And it's easy to see that they are disjoint, right? So how many bad strings I can have? The number of bad strings of length n will be the summation of the number of bad strings of length n minus 1, n minus 2, and n minus 3. And hence we get this recurrence equation for the B series. And since this is an equation of degree 3, we need three initial conditions. B of 1 will be 2 because both the string 0 as well as string 1 do not have any occurrence of triple zero. If I consider B of 2, there will be four strings of length 2 which do not have any occurrence of triple zero, right? And if I consider B3, then there are seven strings of length 3, namely all the strings except 000. All other strings of length 3 do not have any occurrence of triple zero, and hence the B of 3 is 7. Okay, so you can see in this question that why we didn't formulate it directly the recurrence condition for S of n, because that might be slightly involved, but formulating a recurrence for B of n is very easy, and that's why we formulated our recurrence condition or expressed our recurrence condition for S of n in terms of B of n. Okay, right. So in question 3, we want to find out a recurrence relation for the number of bit strings of length n that contain 0, 1. So let S of n denote the number of bit strings of length n containing 0, 1. Again, we need at least one occurrence of 0, 1. There could be more occurrences of 0, 1 allowed as well. My claim is that S of n satisfies this recurrence condition. Let's see why. So it turns out that we can have two disjoint categories of n bits, n length bit string containing 0, 1. Category 1, where the string starts with 1. If it starts with 1, and in order that the overall string has an occurrence of 0, 1, we need that the remaining n minus 1 length bit string should have an occurrence of 0, 1. As per our definition of S function, I will be having S of n minus 1 such bit strings. Okay. And category 2, where the string starts with 0. Now, if the string starts with 0, I may have only one zero, or I may have two zeros, or I may have a sequence of k zeros followed by a 1, and then I don't care what's the remaining n minus k minus 1 substring here, right? And here k ranges from 1 to n minus 1. Why from 1 to n minus 1? Definitely I need one occurrence of 1. Okay. Definitely I need one occurrence of 0. followed by a 1. So that's why k equal to 1. So k basically I am counting here or denoting here the number of zeros which are there at the beginning of the string. So I can have either one number of zero or two number of zeros or n minus one number of zeros. Because I might be having a string of this form. You have 0, 0, 0, 0, 0, n minus one number of time, and the last bit is 1. That's also a valid string in this category too. So that's why my k ranges from 1 to n minus 1. Okay. And then I don't put any restriction. Once I have occupied k plus 1 bits here, so k is the number of zeros and there is a follow-up 1. So I have already occupied k plus 1 bit positions here. The remaining n minus k minus 1 bits can be occupied, n minus k minus 1 positions can be occupied by any bit, either 0 or 1. So how many strings in this second category I can have? It depends upon how many slots I am left here. Because the first k plus 1 slots are reserved for k number of zeros and one single one. So the remaining n minus k minus 1 positions can be occupied by either 0 or 1, and hence I can have these many strings in the second category. So if I sum these two things, I will get the total number of strings. But it turns out that in category 2, my k ranges from 1 to n minus 1. So that's why I have to put k equal to 1, k equal to 2, k equal to 3, k equal to n minus 1. And hence I get total these many strings in category 2. And this is nothing but a geometric progression. If I sum them up, I get this value. And that's how we get this recurrence condition. Okay. Now let's go to question number 4. We want to find out a recurrence relation for the number of ternary strings of length n that has an occurrence of 0, 0 or 1, 1 or 2, 2. Right? It may have an occurrence of all of them, or it may have an occurrence of 0, 0 as well as 1, 1. I need either an occurrence of 0, 0 or an occurrence of 1, 1 or an occurrence of 2, 2. And by ternary strings, I mean that the only characters which are allowed in your string are 0, 1 and 2. Okay. So let S of n denote the number of such ternary strings. The claim is that S of n is satisfying this recurrence condition. So let's derive that. It turns out that we can have two disjoint categories of ternary strings of length n. Let's see them. Category 1, where I take a ternary string of length n minus 1, which satisfies my condition, namely it has an occurrence of 0, 0 or 1, 1 or 2, 2. If I take any such n minus 1 length ternary string, and there will be s of n minus 1 such strings, and if I put any character at the beginning of such a string, that character x could be either 1 or 2 or 3, doesn't matter, because I have already encountered an occurrence of 0, 0 or 1, 1 or 2, 2 in the remaining portion of the string. So it doesn't matter what is my x, it will give me overall a ternary string of length n satisfying my conditions. So how many such strings I can have? So since my x can take three possible values, I have three times s of n minus 1 strings in this category, right? Category 2, where I take an n minus 1 length ternary string which has no occurrence of 0, 0 or 1, 1 or 2, 2. How many such strings I can have? The number of such strings will be all possible ternary strings of length n minus 1 minus the number of ternary strings of length n minus 1 which do have an occurrence of 0, 0 or 1, 1 or 2, 2. Right? So that will be the total number of strings of this form. And let x be the first position of this n minus 1 length ternary string. Right now, there is no occurrence of 0, 0 or 1, 1 or 2, 2. I want to convert this string into a string of length n, which has an occurrence of 0, 0 or 1, 1 or 2, 2. And the only way I can do that is I have to put the same character x at the beginning of the string as well. So that will ensure that the overall length of the string becomes n, and I then will have an occurrence of either 0, 0 or 1, 1 or 2, 2, right? So how many strings of this category I will have? It will be exactly this value, right? Because I don't have an option of x here. Once this x is frozen, right? If this x is frozen, I have to repeat the same x at the first position. So that's why the total number of strings in this category will be this. And if I sum them, these two things, I get this recurrence condition. Okay, right. Let's go to question 5. In question 5, I have defined the function t of m comma n, which is as follows. So you have two sets, a set A whose cardinality is m, and set B whose cardinality is n, and t of m comma n denotes here the number of onto functions from the set A to the set B. Okay, I have to show that t of m comma n is this satisfying this recurrence condition. Okay, so let's prove that. The idea behind the derivation of this recurrence condition is that since a subtraction is involved here, and you can see and identify the structure of this n power m. N power m denotes the number of all possible functions from A to B. Right? It could be either onto or it could be non-onto. So if I subtract all non-onto functions from the set of from the number of all possible functions from A to B, that will give me the number of onto functions. Simple fact, right? So it's easy to see that what this recurrence condition is saying is to derive t of m comma n, subtract the number of non-onto functions. So that means I have to show that this later part of this recurrence condition denotes the number of non-onto functions from A to B. And indeed, that's the case. Okay, right? So while that is the case, so you are given the sets A and B, and we want to find out the number of non-onto functions. So what will be the characteristic of a non-onto function? A function will be a non-onto function from A to B if there is at least one element. There could be more than one element as well, but there should be at least one element from the set B which do not have any pre-image. Or in other words, I can view such functions as follows. I can view any non-onto function as follows, right? So let f dash be an arbitrary non-onto function from A to B. If I focus on the set of possible images which are assigned as per this function f dash and call that set as D, so this is my set D, which is the image set, namely all the elements from the set B which are the images as per the function f dash, then since my function f dash is a non-onto function, clearly this image set D will be a proper subset of B. So more specifically, if the cardinality of this image set D is K, K is strictly less than N. K could be either 1, K could be either 2, K could be either 3, or K could be either N minus 1. If you ensure that, if I take these values of D, then it ensures that there is at least one value from the set capital B which is left and having, which is not going to have any possible preimage, right? So now, in how many ways I can select my set D, right? Since its cardinality is K, I can select it in n choose K ways. And as I said, K ranges from 1 to n minus 1. Okay, so that takes care of the fact that I have to consider a summation from K equal to 1 to n minus 1. Now, once I have decided the value of K, I have to find out which subset or what should be my subset D of size K. So I have n choose K or C of n comma ways of selecting my set D of size K. And once I have chosen my set D, right, the set or the function f dash will be an onto function from the set A to D. That means If I just forget about the set B and just imagine that I have a set D of size k and consider an onto function from the set A to this set D, that can be interpreted as a non-onto function from the set A to the set D because my set D is a proper subset of the set B, right? So now how many such onto functions I can have from A to D? So as per my definition of the T function, there are T of m comma k such functions, right? So once I have decided the set T, I have C of n comma ways of selecting that as per the product rule. For each way of selecting a subset D of size k, I have T of m comma uh, k number of onto functions from the set A and the chosen D set, and hence if I multiply that, that will give me the number of uh, non-onto functions where the image set of those non-onto functions is the set T, right? And then if I, as I said, if I take the summation from k equal to 1 to n minus 1, that will give me the overall number of non-onto functions. Okay, let's go to question 6. Here we recall our Stirling functions of type 2, namely the S of n comma k function, which is the number of partitions of an n element set into k non-empty disjoint subsets, and we have to prove that it satisfies this recurrence condition. So since a plus is involved here, definitely I have to show that I have two different categories or disjoint categories of partitions. Indeed, that's the case. So consider an arbitrary set X consisting of n elements, which I denote as A1 to AN, the elements, and I have to find out in how many ways I can partition this collection into k disjoint subsets, such that if I take the union of those subsets, I get the whole set X, and the subset should be pairwise disjoint. So I can have two categories of partitions. Category 1, where I divide or I partition the first n minus 1 elements into k minus 1 partitions, k minus 1 subsets. That means I am I'm not considering a of n right now. I am imagining that I have only n minus 1 elements and I want to partition them into k minus 1 subsets and then create an extra subset which only has the element a of n. That will now result in total k number of disjoint subsets, whose union will cover the entire set X, right? So how many such partitions I can have? The number of such partitions is nothing but the number of partitions possible for partitioning the n minus 1 elements into k minus 1 disjoint subsets, and as per the definition of S function, this is the number of such partitions. Category 2, where I take the n minus 1 elements and partition it into k disjoint subsets, not k minus 1. Now I have to still put a of n somewhere. In this category, what I am going to do is I am going to consider the case that a of n is going to occupy any of these k subsets, right? So this is clearly different from the case where we have explicitly reserved a whole partition P of k for the nth element, where and the remaining k minus 1 subsets were covering the remaining n minus 1 elements, right? Here, the entire k subsets are going to cover the n minus 1 elements, and a of n also is supposed to occupy one of those subsets, right? So it's easy to see that the number of partitions in this category will be first we have to find out how many ways I can partition n minus 1 elements into k minus 1 subsets. And once I have decided the subsets P1 to Pk, I have the option of either putting a of n, namely the nth element, in P of 1, that's one option, or I have the option of putting A of n into the second subset and so on. So that's why K is multiplied here because of the product rule. Okay, and if I sum these two categories of partitions, that will give me the overall number of partitions. Right. So what will be the value of S of n plus 1 comma n? Right, the number of partitions of an n plus 1 element set into n non-empty disjoint subsets. It's nothing but C of n plus 1 comma 2, because if I have n plus 1 elements, namely a1 to a of n plus 1, and if I want to divide it into n subsets, right? Then that means that there will be only one subset with two elements, and remaining all other subsets will have one element each. So now I have to just find out uh, the two special elements which are going to occupy that subset, which is allowed to have two elements, and that will automatically ensure that the remaining n minus 1 elements which are left, each of them go to 1 1 1 1 subsets. So that's why the answer here is C of n plus 1 comma 2, because there are C of n plus 1 comma 2 ways of picking two elements from n plus 1 elements. So it could be either A1 comma A2, which go together in one subset and remaining all elements go to 1 1 subsets each, or it could be A1 comma A3, which go together in one subset and remaining elements go to 1 1 1 1 subsets each, and so on. Right? That's why the answer is C of n plus 1 comma 2. In question 7, we have to give a combinatorial proof for this identity. So let's see the following setting. You are given n mathematics professor and n computer science professor. You can imagine like that. And say your goal is to select a committee consisting of total n professors, where the head of the committee is a mathematics professor. That's my goal. Now I will show that the number of committees satisfying this goal is the expression both in your LHS as well as in the RHS, right? So why LHS expression satisfies or gives the number of committees satisfying my goal? Because suppose the committee has K mathematics professors, okay, and K will range from 1 to n. Definitely I have to include one mathematics professor because the head will be a mathematics professor, and in the worst case I can have all the committee members being the mathematics professors. In that case, the remaining n minus k committee members will be from computer science. Okay, so that tells you that how many ways you can pick the committee. You first uh, pick the k mathematics professors. That automatically ensures that the remaining n minus k committee members are from computer science. So they can be selected in these many ways. Okay, and once you have decided which K mathematics professors are going to be there and which N minus K computer science professors are there, the committee head itself can be selected out of those K chosen mathematics professors in K ways. It could be either the first chosen mathematics professor or the second chosen mathematics professor or the kth chosen mathematics professor. So that's why you multiply it with K because of the product rule, and that tells you that why the LHS expression gives you the number of committee members satisfying my goal. Let's see the RHS expression. I can say that in order to satisfy my goal, I have to do the following. I have to first select the committee head, and this can be done in n ways because there are n mathematics professors. Okay, so that's why this n here. Now once I have decided the committee head, I have to still choose the remaining n minus 1 committee members, and they can be chosen from n computer science professors and the remaining n minus 1 mathematics professors. Namely, I have still 2 times n minus 1 2 of n minus 1 professors left. I have to choose n minus 1 members out of them, which can be done in these many ways. And now by the product rule, if I multiply the number of ways in which I can select the committee head and the number of ways in which I can pick the remaining committee members, I get the number of committees satisfying my goal. So with that, we end our part 1 of tutorial 6. Thank you.